share my screen. Don't mind the junk behind me. The older you get, the more you collect. Believe me, you can help not collecting stuff, not gathering so much stuff, do it. Because when you get older, it just piles up on shelves behind you. All right. So we're jumping back to Cyclo Edition. The other day we did Cyclo Edition. We talked about stereospecificity. We talked about the conformation of the diene being S-cis. And we also talked about, what else did we talk about? We didn't talk about rate yet. So we're going to talk about the rate today. And then we're going to work a couple of retrosynthesis problems. So let me erase this because we already got that in the notes from yesterday. All right. So now let's jump right in. Let's do this top problem first. Number 2. All right. And in number 2, we have a product, but we need to work backwards to get to the start materials. So the strategy for that is to always start at the alkene. So you always want to start here. Uh-oh, sorry. That's where you want to start pushing your arrows from. So again, with it being a 4 + 2, it's only going to be 3 arrows. And those, excuse me, 3 arrows are going to be, again, pericyclic. So it's only going to move between a certain specific atoms, right? So if we look here at the alkene, if we start at here, boom, that's going to put a double bond, or a pi bond, sorry, here. Right? And then when that happens, I need to break this bond here, which will put a pi bond here. And then when that happens, I also need to break this bond here like that. And that's going to put a pi bond here. Right? And so when we pull that apart, what ends up happening is we end up breaking this sigma bond and this sigma bond. All right. So then my diene is going to look like just a regular diene, actually, in this case, here. And then plus this. And if you notice, none of this other stuff out here got touched, right? We don't touch that. We only care about the 6 electrons that we're moving in that circuit for that pericyclic mechanism. That's it. All right, any questions about that? So the strategy is very simple. Start at the alkene, work backwards, right? In this case, the dienophile is already cis, so you don't have to worry about the stereochemistry or anything like that. All right, so let's look down at the next example here. And you can see the 6-membered ring right here, right? 1, 2, 3, 4, 5, 6. What do we have to think about for this problem with respect to the dienophile? Look at the orientation of the OH group and the bromine, right? They are trans. And so because they're trans, that means that when I break this apart, the dienophile needs to be trans because remember the reaction is stereo specific. Is that right? So we're not gonna do anything different. I know it looks weird because it's a fused ring. It's like a 5-6 system, but I'll show you why in a second. I'll show you why that's the case. All right, so we're gonna take this, push it here, right? We're gonna take this sigma bond, not this one. We're not touching that one. We're taking the one highlighted in pink. We're gonna push that here. And we're gonna take this sigma bond and push it here, like that. You don't touch the sigma bonds here. Those stay intact, right? You should have seen that in the video yesterday about fused ring systems and bridgeheads. That's what we call a bridgehead. I'll show you. And I actually had a 3D depiction in one of the videos showing how these actually look, but I can illustrate it for you here too. So in the star material, this is going to be my diene, and then this will be my dienophile, right? And it's trans. So when I react them together, the groups still have to be trans in that product. So when these two come together, remember, this is homo of the diene, so here, and then the lumo of the dienophile, right here. Right, so when those come together and these orbitals overlap right here and right here, this oxygen is actually going to get pushed up this way, right? Because it's in the ring. So when that happens, you're going to get a, sorry about that. When that happens, you're going to get a 3D structure that looks like this. I'm going to show it to you because you may, if you worked any of the extra practice problems, then you've probably seen that. So you'll have a OH here and then a BR down here. Come on. I don't know why it's lagging, but it is. All right. Any questions about that one? No questions? All right. Let's look at the last couple of questions here, and then I want to work on some other examples off the handout. I wish I could put y'all in some breakout rooms, but I haven't figured out how to do that yet. So I'm not going to waste time trying to learn it now. It says comparing 1 and 3, which one will react faster? So you can increase the rate of a Diels-Alder 2 ways. You can put a, I'm gonna write this out. Right, you can put a donor on the diene. That's one way to make the diene more electron rich. Or since you're working out of the HOMO, or you can put a acceptor on the dienophile. right? So a donor or an electron donor on the diene or an electron acceptor on the dienophile. That's how you increase the rate of a cycle of a Diels-Alder, a 4+2. So if we look at 1 and 3, we have the same diene, right? So that's not going to make a difference. But if you look at the dienophile here and here, what you'll see is that this dienophile has a carbonyl conjugated with it, right? So all carbonyls are acceptors. I'll write this over and make it legible. Right, so all carbonyls are accepted because the reason is because because of this dipole. Excuse me. There's a dipole between carbon and oxygen, right? A big dipole. So it's going to be pulling electron density towards itself, right? So all carbonyls are acceptors. So which one of those is going to be faster? The reaction in 3 or the reaction in 1? Anybody? I know it's Friday. So let me ask it a different way. So if we activated the dienophile in 3, right? 1 is not activated. 1 is just, it's actually kind of slightly deactivated because you got alkyl groups attached to it. So 3 is going to be faster. Right? 3 will react faster because of that carbonyl group attached to your dienophile. All right. Questions? Everybody was quiet on that one. Is it not making sense or what? I mean, let me show you real quick. And then
I was going to say, can you explain it one more time or do another example?
Yeah, let me show you. So here's just a regular diene, right? I'm gonna zoom in so I can, not a diene, but a regular dienophile, as opposed to a dienophile that's say conjugated with a carbonyl, right? One of the things that happens when you put an acceptor on the on the dienophile, especially a carbonyl acceptor, is that you can do resonance. So what that does is it makes this carbon down here positive, right? And now it's activated. Right, so anytime you put a group on the dienophile that's going to activate it, it speeds up the reaction. Right, so if I put a halogen on here like bromine, that's going to cause a dipole this way, and by the same token, it's going to cause more of a dipole that way. So this carbon here is going to be more activated. And when that happens, the reaction speeds up. Right, so if I have something like this, what do you think about that? You think it's going to be even more highly activated? Right, I just put 2 acceptors on there. I put a carbonyl on this side and on this side. So this is highly activated, right? So the more electron withdrawing groups you add to your dienophile, the faster the reaction is going to be, right? Are we okay with the concept of donors and acceptors? I mean, that's something that we learned in part one, but sometimes it kind of slips, right? So a donor is an electron donor. And you can donate electrons through resonance or induction. Same thing with acceptors, right? Acceptors are electron acceptors. Same way, resonance or induction. All right. All right. Let's go on the where's my handout. See if we can work through some of these problems up here. All right. Let's look at come on and focus. There we go. All right. We're gonna do let's do C in 1651. Let's do D and F. Let's do C, D, and F. So what would the product be for, and let me cut this out too right quick. That way we can have room to work. All right. So we're gonna do C. Let's see what I say. C, D, and F. All right. So tell me what you would do for C. You just have to draw the products, but we're gonna put the arrows in too, because that always helps. And tell me what else you have to think about, right? Because there's a couple of things that we have to always think about with these cycle additions. That's the stereochemistry of the dienophile, and then the conformation of the die. Is the die in the right configuration?
Yes.
Yeah, it has to be S-cis, right? So what that means is both of your double bonds are on the same side of the sigma bond between them. So that's fine. What about the dienophile? What's the stereochemistry of that double bond? Is it cis or trans? Cis, right?
Yeah, cis.
Yeah, both groups are on the same side. So it's cis. So then in the product, you put the arrows in and then we'll draw the product. So we're going here to here. Oh, let me ask this question too. So let me draw this out. Because that COOCH3 is the same as this, right? It's an ester. Is an ester an acceptor, do you think?
Yeah.
Yeah, it is. It's got a carbonyl attached to it. And all carbonyls are acceptors. Some of them are better than others, but they're all acceptors. All right. So now let me ask this question. If that's an acceptor, do you think the reaction is going to be a little faster? You actually got two electron withdrawing groups on here, right? You have that carbonyl and you have a chlorine. So this is going to be a really fast reaction because you have a really highly activated dienophile, right? So this is coming here, and this is coming here, right? So the product is a 6-member ring, and then I need to put the pi bond here. The substituents have to be, the stereochemistry has to be maintained because it's stereo specific. Right, so that's fine. And then I have 2 methyl groups that are attached to that side. All right, anybody not see that? All right, let's do F first, and then we're gonna come back to D because D is gonna be a little tricky.
Okay.
All right, let's go down and do F. So F is, it says you have this. I'm gonna change the conformation, and you have it in excess. And that's plus, I think it's this. Yeah. All right. If you have, let me make this simplified. Right. Let's say you have 2 moles of that diene. What do you think is going to happen?
It's
How
gonna
many?
react on both.
Say again.
You can say it's gonna react on both sides.
It can react on both sides. Very good. Very good. It can react on both sides because you have a dienophile here as well as here. Right. So it will, and it's going to react fast because both of those dienes are conjugated with carbonyls. Right. So that's going to increase the rate. So let me put the arrows in. So we go in here, here, and here. And then just for the sake of brevity, I'm just going to put this on this side like that. Right, same thing is going to happen on both sides, basically. So now, let me draw the product out. So this part doesn't change, right? This is still the same. Carbonyl still untouched, right? But now I got a 6-membered ring on this side, boom, with a alkene there. And then I have a 6-membered ring on this side with my alkene there. And that's the product. And the reason is because you have excess dienophile, right? So you got enough dienophile to react more than once. All right, any questions about that? Come on now, wake up, it's Friday. Have some coffee or some tea. Eat a granola bar. Wake up. All right, let's do, I'll have one, it won't get cut. Let's do D. D is a little tricky because it's actually 2 rings reacting together, but we could do it. I have confidence in y'all. Y'all are very smart, bright individuals. So that's the diene, and this is my dienophile. On Russell. It's even worse. Make sure I got it right. Yeah. All right. So do you think the mechanism changes just because the diene is in a ring or something like that? Or it's in a weird structure? Do you think anything changes as far as the arrows are concerned?
No.
No.
No, not the mechanism never changes, right? It's always going to be the same. You can always number your diene and your dienophile to figure out which carbons are going to come together in the product. Right, so let's put the arrows in. We're going from here to here. That means there's going to be a sigma bond between 4 and 5. We're going from here to here. That means that there's going to be a sigma bond between 1 and 6. And then this is moving here, right? So there's going to be a pi bond between 2 and 3. All right, so when we draw the product out, let me show you how to do this in 2D and to make it easier. All right, well, simpler, not easy, because it's not easy, but we can simplify it. Right, we know that this doesn't change. Am I right about that?
Right.
That doesn't change. The structure doesn't change. All right, we also know that we got a 6-member ring that we just made from that cyclo addition. So let's draw that in. Boom, here. Yes or no?
Yes.
And then let's put the numbers back in. 1, 2, 3, 4, 5, 6. Now, where is this carbon here in relation to 1 through 4?
Between 1 and 4.
It's between 1 and 4, and those bonds didn't get touched. So I'm gonna draw that in like this, here and here, right? That's the 2D depiction of it. Are you following? Anybody not see that? Right? Remember, anytime you're doing a 4 plus 2, your core structure is going to be a 6-member ring. So that's what we show here. This is our core structure for that 4 plus 2 cycle addition. Whatever's attached to all that stuff, we just put it back in, right? Right, question, any questions? All right, let's work some, let me cut this so we can have some room. Let's work some retrosynthesis problems. And I'm gonna let y'all go early. Yeah, let's do that. Paste that right here. We're gonna let's work through all of these. Right, I'm gonna draw, let's work through all of them. We got time. Let's start with A. What would you do for A? And we're working backwards now. We have the product. What's the strategy for working backwards with these problems? Remember I said that to attack these problems, these retrosynthesis problems for the 4+2, start at the alkene and just push the electrons backwards, like so, right? What would that give you? That right? See how this arrow is going to put a pi bond here, put a pi bond here, and then one here. So I'll get that plus what?
Plus the
Plus this. Is that right? See how both
Okay.
groups are on the same carbon right here? So in the dianified, they're gonna be on the same carbon.
yeah.
Okay.
Following?
Yeah.
All right. Let's do another one. Let's go to actually let's do C. I'm gonna turn C on this so we can see it in 2D. And then that way that'll make it easier for us to deal with. So that's that. And all right. That's on a wedge, even though I'm sorry, on the dash line, not a wedge. Even though my wedge looks crappy. All right, what would you do? Where are you gonna start?
Start with the alkene.
Start at the alkene, right? That's the strategy. If you gotta dissolve the product, you wanna break it apart, start at the double bond, right? And then push the electrons around that same circuit that you did to make it, right? So this is gonna give me this. This plus, let's do it this way. Plus this, right? That's my diene and my dienophile.
Wait, is that a wedge or a dash?
It's a dash.
Okay.
All right, I'm starting to get it done.
All right. Let's do B. B has the groups on the same side. All right. Nothing changes. If I have the product, and I'm trying to get back to the starting material, I start at the alkene. Boom, 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 right? Those are the bonds that I deal with because those are the bonds I made. I'm breaking this bond, and the pi bond. So my diene looks like this, and my dienophile is cis. Right? Nothing changes. Same mechanism, same process every time you're going backwards. All right, let's do F. F looks like a monster, but it's really not. What are you gonna do on F?
Same thing.
Start at the double
Start
bond.
at the alkene.
Yeah, nothing changes, right? It doesn't matter how fancy it looks. If it's asking you to do the retrosynthesis, this is the process. Boom, boom, right here. Let me fix that. Here, 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 and here. All right. Now, what do we get from that? I'm gonna draw the dienophile first. We get this. Boom. Is that right?
Yeah, that's right.
And then for the diene, even though it looks fancy, it's nothing. It's not a big deal. Nothing fancy about it. That's what the diene looks like. Is that right?
Mm-hmm.
So if I'm doing retrosynthesis of 4+2 products, find that alkene and work your way backwards. Right? I want to do another problem to close out with. I want to do one of the hard ones. Let me see. I saw a problem that I wanted to do. All right, let's do 1655. This is a good problem. It's a tough problem, but it's a good problem. Right here. All right, somebody read that problem if you can, if it's legible.
D's Alder reaction of a mono-substituted diene with a diene with the mono-substituted diene field such gives a mixture of product.
Okay.
Yeah. Gives a mixture of products, but the 1,2 di-substituted product often predominates.
Okay.
Draw the resonance hybrid for each reactant and use the charge distribution of the hybrid to explain why the 1,2 di-substituted product is the major product.
Okay, great. So what it's telling us to do is to draw the resonance forms for the diene and the dienophile. So let's do that, right? And then from the resonance forms, we should be able to figure out why we get one product predominantly over the other. So first, let me put the diene where we can deal with it. Following? So that's my diene. I just made it S cis. And then this is my dienophile. And I'm gonna write that carbonyl out. One day I'm gonna get myself together. I'm gonna write just like the dude on Khan Academy one day. That's my life goal. All right. So the resonance form for this one is gonna look like this. Is that right? Well, those are the arrows. And then the resonance form will be here. Here, boom, like that, O minus H. And then this CH2 down here is positive, right? So we could think about this carbon up here being partially negative. All right, let's do the other. So if I were to do resonance for here, boom. Let me do this. Boom, and then boom. So let's do that, draw that resonance form. Yeah, see it now. All right. So then this is what that resonance form would look like. You'll have a pair of electrons. I'm gonna put the CH2 here. Pair of electrons, negative charge, and double bond O. CH3, and that's positive. And then you have a double bond right here. Is that right? Yeah. Can y'all see that?
Yep.
Yes.
All right. I'm gonna tell you a secret about organic. There's nothing in part 2 that you didn't learn in part 1. Everything it always goes back to the same concepts. So now let's look at these two resonance forms. Right, look at what the major product is first. Let's go over here. You see the major product, what does it look like? You see how the OCH3 group is up here and the aldehyde is here? Right, if you look at the resonance forms, right, if you look at the resonance forms, what do you think? Why do you think that that's the major product if these are the two resonance forms? Think about it. Right? Is that positive charge going to be attracted to that negative charge?
Yes.
Yeah, it is. Right? So if I would have just put the electrons in, right? I mean, you put the arrows in here, you see immediately, this is bam. That's going to happen immediately because that carbon has a plus charge on it. Right? And then this is going to happen. Boom. Here. And then here to that carbon. Right? Followed by breaking that pi bond. That is going to give me that 1,2 product that we see up there. Right? This is based on, again, what you've done is you basically forced the hand of the reaction because you put a donor on the dienophile and then you put an acceptor, right? You put a donor on the diene and you put an acceptor on the dienophile, right? So you change the electronics of the reaction. And in doing that, you get to now pick which product you want to make, right? If you are interested, there's a chemist, his name is Sam Danishevsky. He kind of pioneered the being able to control like the Diels-Alder reaction and the outcome, because he made what's called a Danishevsky's diene, which basically forces your dienophile to come in only one way. So it's really interesting chemistry, and it's all based on the electronics, right? But the fact that now we have a negative charge here based on the resonance form and a positive charge here, those two carbons are going to react immediately, right? They're going to be attracted. And even if we didn't do the resonance, we could just draw it out and you'll see it anyway, if we left it how it was. Right, this is coming here, this is coming here, and then this is coming here. Right, so that's going to give me this 1,2 product, and it's going to be favored because of those resonance forms.
Okay, I have a question.
Come on.
I came a little late. Why did you do the resonance?
That's what it asks us for in the problem. You see right here where it says draw the resonance hybrid for each reactant and use the charge distribution to explain why the 1,2 dot substituted product is the major product.
Okay.
So when we do a resonance, we see that the positive charge in the dienophile ends up on this carbon, and the negative charge in the diene ends up on that carbon. So that's how we know that those two carbons are going to react immediately, because this is all based on charge, right? So that means this carbon is partially negative and this carbon is partially positive. And we know that based on the resonance. All right. Tough problem, but not too bad. Not too bad. Do you think this reaction will be fast?
Yeah.
Yeah. You activated both the diene and the dienophile. Remember I said that earlier. The way you activate the diene is to add a donor, and the way you activate the dienophile is to add an acceptor. All right, we're gonna stop here. I'm gonna let y'all go enjoy your Friday. And I'll post the notes and the video and all that stuff to YouTube, Blackboard, Instagram, wherever I need to post it. I actually closed my Instagram. Instagram is boring.
Yeah, it is.
Yeah, all you just sit and look at people all day. I don't like that. It's not a whole lot of interaction.
Oh yeah, true. I just post my picture and leave.
Yeah, it's like voyeurism, right? Hey, look at me, look what I'm doing. I'm in the hot tub. I'm getting on the plane, walking. I'm eating the sandwich. Look at my dinner. Like, I don't want to see your dinner. I got my own dinner. Anyway, we're gonna stop here. I said I was gonna let y'all go early, so you got 8 minutes to enjoy before your next class, if you have another class.
Is electrosynthesis going to be on the exam as well?
Yeah, it's not a lot though. It's only a couple of problems, and then none of them are as hard as what we just did.
Okay.
So everything that we've covered up to this point, you'll see in some form on the exam. It's a long test too. It's about 35 questions, but it's more substitution and elimination than it is Diels-Alder. And the two, I think there's two workout problems. You have to submit. Please submit PDFs. Don't give me that iPad, Apple, HEIC crap, because I can't open it. And anytime I can't open it, I start throwing stuff. So make everything a PDF, make it simple for all of us. All right, we're good?
Also, for everybody, if you guys can hear me, if you take a picture, you can Google how to take a JPG and convert it to a PDF as well.
All you got to do is use Cam Scanner. You can use Cam Scanner. It'll convert any picture into a PDF. And then there's a Google scanner that'll do it. There's all types of scanners, scanning apps that you can use.
If you have an Apple product, you can do it on Notes.
Yeah, Notes. See, I think the problem with Notes is sometimes people just take the note and upload it instead of turning it into a PDF. That's that. It's a file extension like HEIC, and I can't open that on Blackboard because I'm using